let's take a look at a couple more theorems associated with limits. So our first theorem is this: let f be this function that goes from domain D and has codomain of the real numbers. Let C be an accumulation point of D. Then the limit of f at C is equal to L if and only if for each neighborhood V of L, there exists a deleted neighborhood U of C such that the function evaluated at those points in there are going to be a subset of the neighborhood V. Right? And so that's a lot kind of going on there. It's maybe not quite as bad as it sounds. Really what we have there is V is this neighborhood of L. Right? And so think about within epsilon units of L. Right? So we're thinking about all these values that are within epsilon units of L. And we have this U we can think of as this deleted neighborhood about C. I don't know, let's say we're within delta units of C. Right? And so that is our values of U. It really is just kind of a rephrasing of our definition. All right, let's take a look at our second theorem here. Our second theorem says let F be defined as this and C be an accumulation point. Then we have our limit of F at C is equal to L if and only if for every sequence S sub n and D that converges to C with S sub n not equal to C for all choices of n, the sequence F of S sub n converges to L. Right? And so we can go through and prove this. We'll take some time to prove this. Right, so we'll first go, so this is an if and only if, so we have to go in a forward direction and a reverse direction. So let's suppose that our limit of f of x at C, suppose that limit is equal to L, and let S sub n be a sequence in D. And we want a sequence in D that converges to C with the terms in that sequence not actually being equal to C. So we will show that the limit of f of S sub n is actually equal to L. All right, so what do we know? Since the limit of our function at C is equal to L, what do we know? Well, we know what the definition tells us. So we know that given epsilon greater than 0, there exists a delta greater than 0 such that when our distance between x and C is non-zero but less than delta, we have, this should imply that the distance between f of x and L is less than epsilon. What else do we know? Well, we also know that the sequence converges to C. So since that sequence converges to C, we know there exists some natural number n, such that whenever little n is at least the value of big N, this implies that S sub n minus c is less than delta. Thus, for n greater than or equal to big N, we have 0 is less than S sub n minus c is less than delta, and thus our function minus L is less than epsilon. Hence, the limit of this function is, in fact, equal to L. If we want to go the reverse direction, we're going to roll through here, and we'll suppose in the reverse that the limit at C, let's suppose that it's not equal to L. We will find a sequence S sub n in D that converges to C. So we'll find this sequence that converges to C with terms that are not actually equal to C, but the sequence that we find will also have the property that f of S sub n, this sequence, does not converge to L. Right, so we're going to obtain this contradiction. All right, so we're supposing that our limit of f of x at C is not equal to L. So since the limit of f of x at C is not equal to L, there exists an epsilon greater than 0, such that for every choice of delta greater than 0, there exists an x in the domain with the distance between x and C being non-zero. I always forget that part. Being non-zero and less than delta, such that the distance between f of x and L is at least epsilon, right? So remember, so this might seem a little bit strange, but we're saying that this thing is not the limit. If it was the case that this was the limit, then no matter for every epsilon, there would have to exist at least one delta that would have kind of the opposite thing down here be true. And so since we're saying this is not the limit, we're saying that no matter what delta you might choose associated with any epsilon, or there's a choice of epsilon that you could make. So no matter what delta you might choose, there's going to be a value of x that is within delta units of c, but still has our value of the function more than epsilon units, or at least epsilon units away from L. Right. So we haven't finished our proof yet, but that's what we would have. So in particular, for each natural number n, there exists S sub n in D with 0 less than less than 1 over n, so that the function value at S sub n minus the limit is greater than or equal to epsilon. And so the sequence that we've argued here, this sequence converges to C with terms S sub n that are not equal to C, but f of S sub n, this sequence, cannot possibly converge to L. And so that's a contradiction. And so that reverse implication is also true. All right, so that was quite a bit there. We'll take a look at this last corollary and theorem. We won't expand on them too much. This has been a long video. Let's take a look at this last corollary and theorem. All right, so a corollary to this, if f is this and c is an accumulation point, then f can have only a single limit at that value of d, at c. All right, so we can't have more than one limit at a point. And then theorem 5.1.10. So if we have an accumulation point of d, the following are equivalent. When we say, if we were to say that f does not have a limit at c, that is going to be exactly equivalent to saying there exists a sequence that converges to c, but the sequence of that consists of terms where we have the function evaluated at the terms of that first sequence, that is not convergent in reals. All right, that's it for some limits there. We will talk to you guys later.